be presenting predicting indoor PM2.5 levels using deep learning for enhanced digital twin applications. I'm a research assistant from New York University, and I'll be taking you guys from my research. So let's start with the introduction. So why predicting indoor PM2.5 quality matters? So 80 to 90% of our time, we spend it indoors, making indoor air quality really important and paramount for us. PM2.5 particles, that means like particles that are less than 2.5 micrometers in diameter, they penetrate deeply in our lungs and bloodstream, making, of course, you cannot see those type of particles since they're like microscopical. And indoor PM2.5 levels also fluctuate due to outdoor pollution, ventilation systems, and human activity, of course. And so that's why we created a solution. So an AI-enabled digital twin that has IoT sensors that stream live data in real time, indoors and outdoor data. And we also created a hybrid CNN-BiLSTM that predicts PM2.5 72 hours ahead. And we also created a dashboard that automates the HVAC and also sends occupant alerts. So our related work in indoor PM2.5 forecasting models. So as you can see at the left table, we have plenty of related work on this with different models. So we have BLSTMs, BiLSTMs with self-attention, CNN-LSTMs, informers that are time series transformers. But we see that all of these models only range from 5 minutes to 24 hours. And of course, this is not the best way that aligns, let's say, with building operation cycles. So we need time to be able to verify, to act, and of course, contingency time, of course. So prior studies only forecast just minutes to 24 hours ahead. This is useful for alarms, but too narrow for multi-day planning, let's say. That this is how construction sites work with multi-day planning. So the data and model architecture, so we start with the data collection. So we take 4 variables, essential variables: humidity, temperature indoors, and then we have indoor and outdoor PM2.5. From there, we pre-process this data, so with IQR clipping, that is basically everything that is outside quartile 1 and quartile 3, just we don't take it into account. And AI forecasting using the CNN-BiLSTM hybrid that we created, and the dashboard for air quality analysis. So of course we created a data pipeline for taking all this amount of data in real time, and this hybrid CNN-BiLSTM model captures spatial patterns by the convolutional neural networks and temporal dependencies through the long DLSTM's layers. So, and of course this managed to have an accurate 72 hours prediction ahead. So our variable selection, and why did we choose these variables? So first at the right, you can see the room layout with all our sensors. Our case study was our lab in New York University in Abu Dhabi. So that was basically the layout, and at the left we have the correlation matrix with all the variables who have medium to high correlation, and that's why we chose them. And as you see also, like the key predictors chosen: indoor, outdoor, temperature and humidity, PM2.5. And of course the layout, we try to place all the sensors in the breathing zone height, so to maximize the spatial variance. From there we have the CNN-BiLSTM training pipeline. So we have the data pre-processing, we start merging the indoor and outdoor data, and of course we clean it with the approach that we said before. Then we do a chronological split data set, so it's a 70-15-15, so we have 70% for training, then we have 15 for validation, and the last 15 for testing. So it's completely unseen data, and the results as well, they are really accurate, and they represent the real life, let's say, accuracy. And then we train the CNN-BiLSTM using the atom optimizer and early stopping, as you guys may know already, like this type of optimizations, and we tune it with Bayesian optimization. This is just a mathematical probabilistic method who basically fine-tune the model, and we evaluate on the final 15%. So this is the workflow for training, but let's have a deep dive into the CNN-BiLSTM architecture. So we start with the input layer and the 2 convolutional neural networks that basically extract these spatial features. So that's why we have 2 of these CNN layers, It's a 48 steps, so we take a look back of 48 hours before, and we take 4 feature sequences. As I talked before, humidity, temperature, and PM2.5 indoors and outdoors. From there, we have, of course, the max pool, and then we have the BiLSTM stack these 3 layers, and they go from 256 to 64 units. And you might be wondering, why is this the case? So to progressively learn and refine temporal features from air quality time series, we do it in a hierarchical way. So we start from broad patterns, and then we go to fine-grained insights. So that's why it's really important to have, we start with big layers, and then we start reducing them to have more fine-grained insights. And lastly, we have the forecast head and training. So we output a 72-hour PM2.5, of course, trained with the specification we said before, ADAM and early stopping, and yes. So then we're going to talk about the model performance. So this model performance was done with our data set on the same fine-tuning. So we fine-tune each model depending on the variation optimization. So we had recurrent neural networks, LSTMs, single LSTMs, multi-dense, and convolutional LSTMs. But the one who performed the best were the CNN-BiLSTM neural networks. And surprisingly, the one who performed worse was the multi-dense LSTM. And we managed to achieve good results, 4.8 in terms of PM2.5 units, that is the root mean square error, and 4.0 for the mean absolute error. This data is not normalized because it might sound like a lot, but most of the previous work, this data is normalized, so it only ranges from 0 to 1. But this one is for real life, so we can see the units in PM2.5, so we can make an estimation with that. And then we have the dashboard that we created for real-time insights. So as you can see here, this is a bit of the dashboard that we created for decision making. So we go from real-time forecast to informed action. So the facilities manager can see the 3-day forecast, and of course with that they can take action on the 3 days. So they can see, of course, the air quality forecast with the AQI, and they can see how is it gonna go in the next 3 days, and of course they can also see the performance of the model. That is really important, so they can take all of that into account. And we also create an action guidance for occupants, but also for facility managers to know what to do in case of every AQI category. So if it's good, of course, no action needed, but if it's moderate or unhealthy, they can, let's say, hire the ventilation, air purifiers, even masks if they are needed, and unhealthy, of course, in the same way. So we have an action guidance for the occupants, but also for the facility managers. And we also have some limitations that may arise. So we did the confusion matrix, and of course we have the efficiency of high AQI data, so maybe in the future we'll try to target sampling or even transfer learning to cover these spikes in AQI. And sometimes, of course, there is an overlap between good and moderate classes. This is completely normal in every model because some misclassifications may arise, and on model behaviors or shifting conditions that we cannot really predict or that are not in our data set. So then we're going to talk about future work. So our next steps we're currently working on that is a 3D model implementation. So we want to be able to see, and the facility managers to see a 3D spatial mapping of the PM2.5. So to be able to see a timeline of how the air quality is going to be tomorrow, or how is it going in real time, and of course be able to see the point clouds, the IFC model on top of it. We wanted the facility manager to be able to have all this information, and that's what we're currently working on. And of course, another topic that we would like to also deep dive into it is augmented reality for on-site control. So AR visualization and the superimposed like live forecast and safety recommendations for the facility managers, but also for the occupants, so they can see in real time their spaces, their sensors, forecast, and all of that. So that's really interesting, and we're currently working on that. And thank you very much. So let me know, guys, if you have any questions. And also, thank you, because this couldn't be possible without S.M.A.R.T Lab, Shores, and of course, NYU Abu Dhabi. Thank you.